In this lecture video, we're going to learn about the probability of complements and conditional probability. Specifically, we're going to learn about the probability of at least one and its complement, and we'll discuss the confusion of the inverse. Sometimes we want to know the probability of an event happening at least one time, and the phrase at least one has the same meaning as one or more. When we talk about an event happening at least one time, we are including the idea of the event happening once, twice, or more. That means that the opposite, or the complement, of getting at least one particular event is that you get no occurrences of the event. If at least one includes one or more, then the only thing left for the complement is that that event doesn't happen at all. Let's add some notation to this. If A is equal to getting at least one of the event, then the complement of A is getting none of the event. We know that the probability of an event A plus the probability of its complement is equal to 1. And from this, we know that the probability of an event A is equal to 1 minus the probability of its complement. So the probability of A in this case, or at least one occurrence of the event, is equal to 1 minus the probability of getting none of the event A. It's often easier to calculate the probability of none than at least one. So we can use this relationship to help us calculate the probability for at least one. Let's take a look at some examples. For each of these events, we're going to write a written description of the event and its complement. Then we're going to find the probability of the complement of the event. Our first event is the idea that a couple has 5 children and all 5 are assigned female. Let's label this event capital F, and we'll describe it as the event of all 5 being assigned female. Based on that, let's think through what the complement of F would be. Think about the fact that having all 5 children be assigned female can also be thought of as no male. And the complement of not having any children assigned male would be having at least one assigned male. And using our language for event F, we can express the complement of F as the event of having at least one not assigned female. Now we need to calculate the probability of the complement of F. We need the probability of at least one not being assigned female. The probability of the complement of F is equal to 1 minus the probability of F. And finding the probability of F is much easier than finding the probability of the complement in this case. Consider that to find the probability of at least one not being assigned female, that's at least one child being assigned male, we would need to take into consideration the event of one child being assigned male, 2 children being assigned male, and so on all the way up to 5. That's a bit more of a task than simply finding the probability of all 5 being assigned female. So let's find that probability of F. The probability of the first child being assigned female is 1 over 2, and the probability of the second child being assigned female is also 1 over 2. It's the same for all 5 children. They have approximately a 50-50 chance of being assigned male or female. This is equal to 1/2 raised to the power of 5, or 0.0313. And having that, we can calculate the probability of the complement. That's 1 minus 0.0313, or 0.9688. Now let's look at this next event. This is the event that when 4 digits between 0 and 9 inclusive are randomly selected with replacement for a lottery ticket, at least one of the digits is 0. Notice we have the phrase here, with replacement. This is the idea that after a number is selected, it can be selected again. We don't have to have unique values for each of the 4 digits. Let's label this event with capital A and describe it as at least one digit is 0. Now we need to think through what the complement of event A must be. If the event A is at least 1, then the complement is the idea of none. With A being the event of at least one digit being 0, then the complement of A would be the idea that none of the digits are 0. Now we need to calculate the probability of the complement of A. Notice that in this case, the complement is the event of none, which is the easier probability to calculate. So in this case, we will not be using event A as part of our probability calculation. What's the probability of the first selected digit not being 0? We have 10 choices in total, from 0 to 9 inclusive, and 9 of those are non-zero. So the probability of the first digit not being a 0 is 9 divided by 10. And we have that same probability for each of the 4 digits. So the probability of none of them being 0 is 9 divided by 10 raised to the 4th power, or 9 divided by 10 multiplied by itself 4 times. This gives us 0.656. So the probability of selecting 4 digits that are not 0 is 0.656, or about 65.6%. Let's take a look at a slightly different example. Here we have a company that supplies DVDs in lots of 50 with a defect rate of 0.5%, which is 0.005 in decimal form. A quality control engineer is hoping to select a defective disc to analyze it. What's the probability that in a lot of 50, they will get at least one defective disc? We're going to assume that selections are made with replacement. That means there's the same probability of choosing a defective disc each time. The key part of this example is the question of what is the probability that in a lot of 50, they will get at least one defective disc. Let's describe this as our event D, and that will be the idea of at least one disc being defective. Calculating the probability of event D can be difficult because to calculate the probability of at least one, we would need to take into consideration the probability of pulling one defective disc, 2 defective discs, 3 defective discs, all the way up to 50. So let's instead use the complement of event D to calculate this probability instead. The complement of D is that when pulling 50 discs, none are defective. This is a more straightforward probability to calculate. The probability of this complement can be found by using the defect rate of 0.5%, or 0.005. If the probability of pulling one defective disc is equal to 0.005, that means that the probability of pulling one not defective disc is 0.995, or 99.5%. We want to know the probability of pulling 50 discs that are not defective. Well, the probability of pulling one disc that's not defective is 0.995. And if we replace that disc, the probability of pulling another one that's not defective is again 0.995. And we repeat this 50 times. So what we really have here is 0.995 raised to the power of 50, or 0.778. Now that we have the probability of the complement, we can get back to calculating the probability of our event D. The probability of having at least one defective disc in this lot of 50 is 1 minus the probability of not having any that are defective, or 1 minus 0.778, or 0.222. Now we are ready to talk about the big idea of the confusion of the inverse. This is the idea of incorrectly stating that the probability of event B occurring given that A has already happened is the same thing as the probability of event A happening given that B has already happened. These are not the same thing, but they are often confused and incorrectly used for one another. Take a look at this example statement. Hard drug users use marijuana, therefore, marijuana users use hard drugs. Think about that for a moment. Are those two things the same thing? They're not. The first part of this phrase, hard drug users use marijuana, is the idea of the probability of a person using marijuana given that we already know they use hard drugs. The second part of this phrase, marijuana users use hard drugs, is the idea of the probability of someone using hard drugs given that we already know they use marijuana. Let's write this down in a more specific way. First, let's let H represent the event that a subject is a hard drug user. And we'll let capital M represent the event that a subject uses marijuana. The first probability of marijuana given hard drug use can be expressed as the probability of a subject using marijuana given that we already know they are using hard drugs. And the second probability, hard drug use given marijuana use, is the probability that a subject uses hard drugs given that we already know they use marijuana. These two are not the same thing, and this is exactly what we mean by confusion of the inverse. So when you're calculating conditional probabilities such as these, make sure you know which event is which and which event is being assumed to have already happened. That concludes this lecture video on the probability of complements and conditional probability.